Next speaker will be Reza from ASML, and he will be talking about missing data, which is, I think, a very common problem. So if I'm not mistaken, do you you have a background in speech recognition, right?
Oh, yes, I do. Yeah.
Yes. So is this similar to the work you're currently doing at ASML?
What? The speech one?
Yeah, the speech recognition.
Not at all. Yeah, because the missing data problem is not actually a problem in missing in speech. We usually have a huge amount of speech available, and that was not a challenge when I was a PhD student, and that was a challenge actually I encountered when I came to industry. Yeah.
Okay.
Yeah.
Interesting. Well, the floor is all yours.
Thank you. Yeah, of course. All right. Well, thank you for the introduction. Today in this presentation, I'm going to talk about one of the maybe most common issues or challenges that you may face, so long as you work with real data or industrial data, and that's missingness. And the reason that I've chosen to give this presentation today is that, first of all, as someone who works with ASML, well, we work with a lot of missing data. You know, the majority of the big part of the data that we work with is coming from ASML machines, and for a number of reasons, we do not always have all the measurements available. For example, some measurements are very expensive, and we don't want to do that for all the wafers or samples. But more importantly, and maybe more generally, as a data scientist or engineer or deal with missing data. And I believe it's not some optional skills you may want to have or not. It's a necessity. And as an implementer or, well, particularly Python user, you also need to know what's happening in the packages you use or what's happening behind the scene in the code. And here are two examples that I hope is going to make you motivated to listen to me for the rest of this presentation. So one of them is about three of the common packages in Python random forest from scikit-learn, light gradient boosting method, and extreme gradient boosting method. And these packages actually work totally differently towards missing data. One of them, the scikit-learn one, returns error. It doesn't work with missing data. And the other two, like light gradient boosting by default replaces 0 by missing values, which I would say it's not really smart. And the last one, extreme gradient boosting, does something fairly smart but ad hoc to its own structure. Or two other operations, popular operations, especially in image processing, like max pooling and average pooling from a subclass of layers in Keras. One of them simply ignores missing values, and the other one considers that. So the key point here is that we need to be vigilant about even the code that we make regarding the way it works with missing data. So in this presentation, and the way that I'm going to forward today is to first take one step back and talk about missing data, maybe more fundamentally, the reason that it happens and why it's important to be careful about it. And but maybe the most important part is the type and the origin of missingness, because the approach that you're going to take to deal with missing data really depends on the information you can collect by knowing these things about your data. And I'm going to also talk about methodologies that you can use to work around missing data problem, but I'm not planning to go technically into one or two methods, because simply there is no one-size-fits-all solution for missing data. And usually to be able to choose the right method, you need to actually have a good understanding about your data to actually find the one which suits you the best. I'm going to also show you some examples. I have some notebooks, Jupyter notebooks, that I'll make sure you will have access to. It's on Google Colab, so you can simply rerun it. And especially if you have not done much in the missing data imputation before, it's going to be great a start for you to get acquainted to some open toolboxes like scikit-learn or fancy impute to do the imputation. All right, why missingness and where it comes from? Well, there are a number of reasons for that. As I said, at ASML, for example, cost or expense is one important reason that we have missing data, but there are other reasons too, like, I don't know, the privacy or even the fault or mistake from the machine or the human who collects the data. But the more important question we should ask is that why we should care about missing data. And I would like to view it in two ways. That one side of the story is that majority or almost all of the machine learning or AI, data science related methods are developed relying on the assumption that the data is complete. And if you have incomplete data, you need to find a way to map the incomplete data to a complete one. And another side of the story, which is, well, equally important, is to be able to do the imputation or to fill in the missing values with the right and accurately enough candidates, because we don't want to mess up with your data by adding noise or bias to the data set. And to be able to find the right way, we need to, the first step is to understand the types of the missingness. And it's, well, according to many of the literature, a big part of the literature, it can be categorized into three groups. The first one is called missing completely at random. And in this case, there is no particular reason that data is missing, but also there is no relationship or dependency between the observed variables and the missing, the valuable variables with missing values. So in this case, I've made a handmade example, assuming that we had a questionnaire asking some participant to fill in some information about their salary and their gender. And in this case, two people didn't mention anything about salary. So there is no, I mean, the data doesn't suggest that. And also we don't have any prior knowledge that men or women are more inclined to talk about salary. And also let's hope that we are living in a world with no gender discrimination. So we cannot make any guess or estimate of the salary according to the gender. Then this is called missing completely at random. And for the missing at random one, well, as confusing as it sounds with the first one, there is a huge difference. And in this case, there is a correlation or dependency between the missing values and the observed ones. So in our example, if we ask the participant to tell us how experienced they are, then both the data and our common sense tells us that there is a relationship or correlation between the amount of the salary and how experienced someone is. So this is called missing at random. And the last one is called missing not at random. And this is the most difficult one because in many cases we can't do, or let's say we cannot make a good estimate for the missing values because we don't have enough information about that. And in our example, let's assume that we ask the participant for their positions in the company, and we realize that whenever the person is a CEO, we don't have any information about the salary. So there could be a reason for that, but we are not aware of it. This could be, for example, CEOs don't have a fixed salary, or they don't want others or us feel bad about their own salary. Either way, we don't have enough information to make a good estimate of that. And before going further, I would also like to make some points. First of all, distinguishing the type of the missingness is not easy, and sometimes it's even impossible. And sometimes our data has a number of kind of, let's say, missing data. And these are all sources of confusion and complication. And that's why, that's one reason that missing data can be very challenging for your task. And also, before trying to distinguish the type of the missingness, you need to be sure that you know enough about your data. The data is complete enough or is balanced enough. And just maybe as a rule of thumb, you will find that in many cases, people already assume that the data is missing at random, just to make life easier for themselves. But obviously, this is not an accurate assumption. So how to deal with missingness? If we should, and that means that if you have enough information to do the imputation or to take any action, obviously one scenario is to drop or ignore missing values. And I particularly mentioned the art of dropping because as maybe it sounds trivial, but it actually is not, and it can really be very tricky and dangerous. And to be able to make this important decision, whether to drop or ignore the missing values or not, you need to have a good understanding on many factors around your data, like how much information you would lose by removing or dropping those samples. And if there is another or better approach to take. The other kind of action that you may take is to impute, and that means to fill in the missing values with some, let's say, guess or estimation. And this can be done generally in two ways, which are called single imputation and multiple imputation. The single imputation, as the name suggests, simply provides us with one version or one imputed version of the incomplete data. So in this case, the red square shows the missing entries, and it's imputed by the single imputation. Multiple imputation does that multiple times. So simply, instead of having one version or one imputed version of the data, we have multiple imputed version. And this is actually to account for the uncertainty of our guess or estimate for the missing values. And if you wanted these, let's say, the new set of data sets in your task, in the machine learning or data science task you have in your hand, you may either apply your analysis on all of these data sets individually and then do some combination and pooling in the end, like what you're doing on some learning, for example. Or if you want to train a neural network, for example, you can simply let the neural network be trained on all of them together. In that case, you are transferring the uncertainty from the data to the parameters of your neural network. The other way to let's say, categorize the methodologies for imputation can be viewed as the model that you use. It can be either discriminative models or generative models. In the discriminative models, you already assume that there is a correlation between missing variables with missing values and the observed variables, and that's why you want to actually find this correlation by estimating a function. But for generative models, you may what you want to do is to estimate the distribution of the data, the variable which has missing values. If it's completely at random, then only the normal distribution. But if it's missing at random and there is a dependency between observed and variables, you may estimate the conditional distribution. As for the single imputation, well, maybe this is the most common type of imputation we do. As I explained, we want to have one version or one complete version of the data, and there are a number of approaches. You can just go to the literature and you'll find tens of them. Well, some examples are mean or median imputation, simply looking at the observed values and then take the mean, fill in the missing values. You can use K nearest neighbor or KNN approach. In that case, you consider a neighborhood for the sample with missing values and do the imputation according to the samples in that neighborhood. Or you may benefit from some predictive or discriminative models, like linear regression, neural network, random forest, whatever it is. You simply look at the data, the complete part of the data, and you want to train a model which maps the observed variables to the variable with missing values, and then use that model to do the imputation whenever data is missing, right? And there are a number of other methods too, like matrix completion. You may benefit from PCA or expectation maximization, but no matter what method you use, as long as you're doing single imputation, you don't account for uncertainty. And like I said, one popular approach to cope with that problem is to benefit from multiple imputation. And there are a number of ways to do so. For example, bootstrapping, by subselecting the data from with replacement, of course, and do the imputation, do the subselection again, do the imputation, and just continue like that to have number of imputation version. Or generative models, as I said, you estimate the distribution, so you can draw samples from this distribution, and you can draw multiple samples to fill in the missing values. You may benefit from multiple imputation techniques or discriminative models, like one version is coming from neural network imputation, the other from random forest. And even in any of some of these methods, you can already play around with the random seed parameters to have multiple versions of imputation, even using one discriminative models. And there are other popular techniques too, like MICE, which stands for multivariate imputation with chained equation. This is actually a very popular one, which is used in industrial application. And the way it works is that it does the imputation in a round robin fashion. So it starts from the incomplete data, it does some initial imputation like mean imputation. So in the cycle one, it just focus on one variable. It tries to estimate the missing values according to the observed one, then go to the next cycle, fix what is being imputed in the first cycle. Then in the second cycle, it goes to the next one, does the imputation for that, and continues until all the variables are imputed. And you can do the same thing from scratch multiple times to have multiple versions of the imputation. Or in the denoising autoencoder, what you do is to benefit from an overcomplete autoencoder. It's a black box model. It's a neural network which takes the well, the input is the missing value or the incomplete data, where the missing entries are filled in with some random noise, and it learns to map that to the complete data, right? And in the test, you can benefit from that for imputation. So there are two, well, actually there are many, but there are two, let's say, challenging yet very practical and helpful topics I'm personally very excited about, and I want to talk about them in this slide. One of them is exploiting target or output for imputation. And when I'm saying target or output, I mean when you have a task like classification or regression, then you want to estimate or predict something that's called target. And you can already say that it's not as straightforward and can be very difficult, because target is the most mysterious type of missingness that we want to estimate at the end of the day. And but there are some scenarios and situations that we actually this target can be helpful, but maybe indirectly in the training phase at least, to have a good imputation. And I don't want to go to all the let's say details of that, but just to give you an idea that how it's possible, I would like to show you, actually talk about one example, which is extreme gradient boosting method. Well, this is the one, actually, if you use the package, it does the imputation according to that. And well, it's a decision tree based method. And so what it does is that when the model is being trained, you're actually training a threshold for each node. And let's assume that we have only two split at each node. So when the variable comes, the parent node, then we want to decide whether to go to the right or to the left. But if the variable has missing values, what the algorithm does is that it goes on both sides, and it calculates the loss function values for both sides. So in the end, and the loss function is considering the target, right? So in the end of the training, you have two loss function values for both sides, and the one which is smaller is going to be considered for the default. So the direction which actually resulted in the lower loss function value will be considered as a default, and in the test phase, that direction will be used whenever that variable has missing values. Another issue is availability of the complete data. For majority of the algorithms or techniques I talked about so far, we need to have access to the complete data, like, for example, the denoising autoencoder. But in practice, sometimes it's even impossible to have the complete version of the data. And it's important to somehow benefit from even the incomplete version of the data during training. And there are, again, it's a very active area. It's an interesting and active area in the community. And just again, to give you an idea that how it might be possible, I'm going to refer to one example, which is based on generative adversarial neural networks. For example, GAIN, or there is another approach, it's called misgen. You may refer to them. They are fairly new methods. So what it does is that next to the data, it considers another data structure, which is called mask vector or mask matrix, which represents which entry is missing and which one is there. And then the generator in the GAN framework, which is the imputer actually for us, does the imputation. But since we don't have access to the real version or the complete version of the data, the discriminator or critic cannot look at that one, but it looks at the mask vector and it tries to estimate the mask vector. And how good the discriminator can make the mask vector means that how good or bad the generator worked. So this is just a brief overview of the algorithm. Of course, the way it's being implemented as being proposed is a bit more complicated, and but hopefully you have the idea that how you can turn the problem so that you can benefit from the incomplete data too. All right, and in the end, I want to show you some results, illustrative results from MNIST dataset, which is a dataset of images of digits. And I have used a scikit-learn imputer and fancy imputer, two open source toolboxes, actually with number of interesting imputation techniques. And these are the results from the notebooks I said will make it available for you. So you can simply reproduce these results yourself. So what I did was that I artificially induced induced 20% missingness in the data, as you can see in the bottom. And then I tried number of imputation techniques. So for the single imputation, I tried like median, mean, and KNN imputation. And you can already see that, for example, a median or KNN works better than the mean imputation. And you can do that with both scikit-learn and fancy impute. The other one is mice and denoising autoencoder. These are multiple imputation techniques. For the mice, I use fancy impute, and it adds some artifacts according to the estimator you use. And the noising autoencoder is implemented with Cross, you'll see in the notebook. And you can already see how well the noising autoencoder works with imputation. And finally, the generative adversarial method, which is the gain imputation. And in this case, the difference is that the training data didn't have the complete version of the data. So all the data, including, test and train both, had missing values. And it's somehow impressive that even with that, it can generate the samples like this. So again, for the gain imputation, also, I'll make a separate notebook available. So for those of you who are maybe more advanced in imputation, then you can refer to that. All right. As a takeaway, or let's say the conclusion, maybe the most important thing that I would like to emphasize is that when you're facing missingness in your data, before choosing the algorithm or the methodology to work around it, you need to have a good understanding of your data. What is the missingness type? What are the other factors like the size of the data? If there is a correlation between observed variables and missing variables or not. And then go to find the right method. There are a number of them available out there. Also, I would like to suggest you to look at multiple imputation more because, well, of course, it's going to come with extra work and maybe extra computation, but sometimes it's the only way to actually consider or account for the uncertainty of your imputation. And be careful about the open source toolboxes you use. Some of them, because of the, missingness is a common issue. So some of them do some default action. So be careful about them. Do not leave it up to your packages to decide for you what to do, but do it yourself. And if you're interested in more, let's say, advanced methodology, check the literature. Very high-rank conferences like ICML, NeurIPS, every year you can see a number of interesting papers in missing data imputation. All right, that's it. Yeah, so we have enough time maybe for some questions.
Yeah, for some questions. I do have a question myself, and I hope you're familiar maybe with this. I think Andrew Gelman, he also wrote in his book about data imputation, and he's doing something very specifically there. So what he's doing, he's saying, okay, you shouldn't impute with an expected value because the data won't look like the original data anymore because the noise is out.
Mm-hmm.
So he then adds the random noise into the data.
Mm-hmm.
So what are your thoughts on that?
Yeah, that's a good point. Actually, one of, this is maybe, well, that reminds me of a comment I received from a colleague of mine, said that we are not magicians. We are not supposed to create what doesn't exist. But the reason that we need to do imputation, as I mentioned in one of the earlier slides, is that sometimes we have to do that because, for example, if we want to benefit from methodologies, AI methodologies, or modeling techniques, which are coming on daily basis these days, many of them rely on the assumption that data is complete. So if the data is incomplete, we have to somehow find a complete version of that. Otherwise, we cannot do anything. We cannot benefit from the algorithm which is out there, and we need to do that. So we just have to be careful not to add too much noise or bias on the data. And that's actually a good question, because my hope was that to convey this message that be very careful about the missing data imputation you use by collecting enough information about the structure of the data, the type of the missingness, and by that you may reduce the amount of the noise or bias you will add to the data by imputing.
Yeah, so basically you're saying if you have to do imputation, you always introduce some kind of bias into your data, so you should be very careful on how you do it.
Exactly, yeah.
So I don't know whether you have any experience with whether you should or should not be adding additional noise in your imputation, but my line of thought here is that it might actually be a bad thing to do, because it could be, if you do some kind of inference, for example, that you introduce some new biases. You have a thing called measurement error or attenuation bias, and actually because you're adding noise to the model, your effects that you get out of the model, they tend to be closer to zero.
Right.
So it maybe depends a little bit on whether you're doing inference or doing some kind of machine learning.
Yes. Also, it depends on what you're going to do instead. I mean, if you don't impute, what's the next option? Ignore them, or use a methodology which is capable of, I don't know, benefiting from missing data, like extreme gradient boosting, for example.
Yeah.
If it's ignoring, then again, it's important to know, if let's say you have 2 examples with missing data out of thousands, then it's safe to not impute and ignore them and do your inference or modeling, whatever you want to do with the rest of the data. But if it's 50% of the data and you just want to remove them, you're removing or ignoring half of the information in your data. And maybe then again, it's up to you as a scientist to engineer to decide which one is more dangerous, right? Imputing and adding some noise, or removing and being totally blind about the information in that part. Yeah. So there is, as I said, there is no one size fits all solution. So it's at the end of the day, it's up to you to decide what is not, let's say, the best, but what is the
least worst
technique to cope with missing data.
Yeah, it's really interesting, especially like filtering data out. It takes a really strong perspective, because you can say, oh, I have enough data anyways, but you can induce the bias by kicking the other data out. Right?
Yeah. Very good point. Yeah.
Okay.
Yeah.
Perfect. So I'm taking a look at the time. We don't have the clock anymore. Yeah. So we finish a little bit early, I suppose.
All right.
But that's not a problem. Thank you very much for your talk.
Thank you very much
for having me.
We're already
having a conversation about it. That it was a really great and clear
very nice
talk.